Hello class, this is Professor Kamen, and this is part 2 of processing metals casting. Let's go ahead and get started. And so we're going to move on to evaporative sand casting. Now another name for evaporative sand casting is called lost foam sand casting. And the reason why it's called that is because you use materials that are essentially foam and then they essentially disappear. So this is the way it starts out. You have a pattern. The sprue and the riser are all made up of a type of polystyrene, which is similar to styrofoam. Okay, and this styrofoam is foam from pellets, and then it's made into the pattern, and it's coated with a thin layer of refractory material. Sometimes it's called a slurry or some type of ceramic material. So this material, remember, is refractory, which means it helps it to hold up against very, very high temperatures. The next step is that you pack dry sand around that pattern. So there are the polystyrene pellets that are formed into the pattern. Here you can see kind of some examples of some common products here. It looks like a wheel rim. This is an impeller, like I told you before, from a pump. And then you have another manifold, possibly from a car. Here are examples maybe of gears, patterns for gears. And what happens next is that this molten metal is poured into this, and the polystyrene pattern instantly vaporizes. Okay, instantly turns into a gas, and that leaves a cavity in place, and that's what the metal fills. So you can see how closely the pattern represents the final product. Here's another diagram of the basic process of evaporative sand casting or lost foam sand casting. You start with a pattern, oftentimes in very high throughput processing. You have what's called a cluster assembly, or it'll be called a tree assembly, in which you have several patterns essentially all put together on in one group. Then you coat it with the refractory material, and you put it in a box and you support it with sand. All right. The next thing you do is you pour in your molten metal, and then again, as the molten metal hits that polystyrene pattern, it instantly disappears or volatilizes, turns into gas, and then you have your molten metal to cool into that area that's left over. So what do you think is one advantage this process has compared to green sand casting? And when you think about that, keep in mind that in this case, you don't have to remove the pattern because the pattern disappears, volatilizes. And so what does that mean? Well, first of all, you can cast patterns of any different size and shape, right? Because the pattern doesn't have to be removed, so you don't have to worry about a draft. You don't have to worry about how am I going to get this pattern out of this mold, because it instantly volatilizes. Now, mold shift problems, which are a big problem when you're dealing with sand casting, green sand casting in particular, they're eliminated because mold shift occurs when you're removing the pattern or when you're putting the pattern in. And so this doesn't have to happen anymore. And so you don't have to worry about mold shift. It's very low cost to prepare the sand. You don't need any binders or additives. And this is economical for prototyping or for mass production. Our next type of casting process is called shell process sand casting. This process is actually interesting because it can be considered a semi-permanent mold casting process. So what happens? Well, a permanent metal pattern, so you have a permanent pattern, is used and it's heated. And then that pattern is coated with a release agent to make sure that any sand that dumps on it can actually be released from it. Then you return it upside down in this big, huge box and allow that sand to fall on it. And then that sand sticks to it and then it hardens. Now, after a certain amount of time, the dump box is turned back over again. And then that pattern, which is really just a layer which has formed to the pattern, rather, the layer that has formed to the pattern comes off, right? And then it looks like a shell. And so you have essentially half a shell. So you do that one more time. You put the two halves together, and then you have a whole shell. You put that in a box with some sand around supporting it, and then pour your metal down in between the two. So this is kind of what it looks like. Here, so here's a diagram. You have your big, it's called a dump box, okay? You have your sand at the bottom. Now here's your metal pattern right here. You invert the dump box, turn it upside down, and then all that sand falls on the heated metal pattern. Because the metal pattern is heated, it goes and starts to solidify the sand just in a small layer right here. You turn the dump box over again, and then you still have that layer of sand, that shell. Then you remove the shell, create another shell, and you have two halves, and then you support that with sand, and then pour your molten metal in between here and allow it to solidify. Now, the reason why this is a semi-permanent mold example is because these shells can be used over and over and over again. They do wear out after time, but they can be used on a semi-permanent basis. So here's a quick illustration of the shell molding process, shell process casting. It's called shell molding or shell process casting. So you see the dump box turned back over again. Here's the metal pattern. Here's the shell that was created. Okay, so now you have two of those shells, and you dump the sand behind it, and then you pour the molten metal in there. Now, the only thing that is wrong about this is that it looks like you just completely get rid of the shell, which does not happen. See, it doesn't show you the shell here, but that is what happens. The shell continues to stay around. Okay. Now here is another video discussing shell process sand casting. Let me start that one over again.
Shell molds for sand casting are produced by heating a metal pattern and then rotating it upside down. This exposes the pattern to a mixture of fine silica sand and a resin binder, setting a layer of the mixture to the heated surface of the pattern. To complete the curing process, the coated pattern is covered and baked. Once cured, the hardened shells are removed from the pattern and serve as mold halves. Shell cores, which are produced similarly, are placed within the drag side of the mold. A bonding adhesive is then applied, and the coat side of the mold is aligned and secured, creating the finished shell mold. These shell molds can be produced quickly and store well for extended periods of time. Shell mold casting is a semi-precision process, permitting more intricate shapes, closer tolerances, and smoother finishes than using green or no-bake molds. The size of parts that can be cast in shell molds is limited, however, with most castings weighing less than 45 kilograms.
All right, so what are the advantages and disadvantages of the shell process casting process? Well, this process has advantages in that it gives you finer detail and a smoother finish. And the reason why it does that is because the sand is finer, and it also makes a smoother mold surface. Now, part of that is also too because you have a semi-permanent mold. So semi-permanent molds and even permanent molds, so the more permanent it is, it will give you a finer, smoother surface with higher dimensional accuracy. Now, number two, the mold is very strong, okay, allowing the casting for parts with fine details. So we just mentioned that. The molds have a long shelf life. That's why it's semi-permanent. It just isn't just one use. And then it also gives you a good repeatability. So you're able to repeat products of the same dimensions with this process. Now, what are disadvantages? Mainly is that it costs a lot. Okay, these core boxes or these dump boxes, they cost quite a bit. And because of that cost, purely because of that cost, these are only economical for a high quantity production. All right. Also, you have a little bit of saving on machining afterwards because of its superior material properties afterwards. It's finer and higher dimensional accuracy. But in the end, it has a very high cost, which only makes it economical for high quantity production. All right, now let's look a little bit closer about permanent molding versus non-permanent molding, which we'll call sand casting. And of course, you have the shell process kind of in the middle because that is a semi-permanent molding casting process. All right, so first of all, how can we describe permanent molding? Well, permanent molds, they can be used and reused and reused and reused, okay? So that is an advantage. But these molds are made by machining, they're finished and polished, and then they have refractory typically added to them to prolong life. Now, we haven't specifically talked about any permanent molding casting processes yet, but we will directly after this. And number three, they give a good surface finish and very high dimensional accuracy. And this is because it is a permanent mold. All right, let's look to 4. Now, because it is a permanent mold, it has a very high mold cost. You can remember from part number 1 that we talked about how green sand casting was very cheap. Well, permanent mold have a very high mold cost, very high to make those molds, very high to maintain those molds. Also, you can have limited intricacy in casting shape for these permanent molds because they're based upon the shape of the mold that you can make. They're also not good for high temperature metals. Okay, why are they not good for high temperature metals? Just because those metals or the heat from high temperature metals, that means high melting temperature metals, can damage the permanent mold. And then once the permanent mold is damaged, and then you have to really create another one. All right, now let's look at more versatile sand casting. So for sand casting, you have to make a new sand mold each time you want to cast. So that is a definite disadvantage, okay? But because you're sand casting, you're going to have the same dimensional accuracies of that sand. For number 3, just about any metal at just about any temperature. So that's definitely an advantage because of the refractory properties of sand. Your melting temperature of the metal doesn't really matter that much. It's not going to hurt the sand. That's why you can do any metal at just about any temperature. Okay, so our first permanent mold casting process is called centrifugal casting. And this is how it works. You have a molten metal that's poured into a rapidly revolving mold. Okay, so obviously this is going to be for molds that are cylindrical or circular in shape because it's going to be rapidly revolving. Then, due to the centrifugal forces, the metal is going to conform to the shape of the mold. Okay, so think of something like a merry-go-round. If you guys remember a merry-go-round, what happens is somebody stands in the middle, somebody stands on the side, and they go ahead and swing you around. Okay, so as this thing keeps going faster and faster, spins faster and faster, you can feel yourself being kind of pulled off of it. That centrifugal force is pulling you off of it, and the same thing occurs when you have centrifugal casting. So other things to think about. Your cooling rate, okay, is going to depend on how thick the mold needs to be. So both of those are intertwined. Slag, which is a certain amount of impurities, can collect on the inner wall and can be removed by machining. This is actually an advantage because all those impurities can be removed at once and give you a very pure casting. This can be done horizontally or vertically, whether you want to produce wheels, drums, barrels, pipes. Of course, these are all cylindrical or circular products. So here's an illustration of how centrifugal casting occurs. So right here is your machine that's holding your permanent mold. And then they're going to do some things first. So they're going to apply a mold coating to the inside surface of the mold. All right. You can see it's spelled M-O-L-M-O-U-L-D, so it's probably European video. But the reason why they're doing this is to prevent chilling and also to make sure that that mold solidifies evenly. Okay. Now you also want to provide a good surface finish, and this enables easy extraction. So it enables you to extract the mold very easily. Next, you're going to pour in that liquid metal, the molten metal. Metal goes in as your mold is spinning. Okay. So the molten metal is subjected to 80 to 120 times the force of gravity. That's that centrifugal force we are talking about. Okay. Solidification is going to take place from the outer wall to the inner wall. And because of that centrifugal process, the heavier or the more dense materials will go to the outside. That's the metal. The less dense material is the slag. And machine that off, this gives you a very pure metal structure. Okay, so advantage is very pure structure. That gives you better mechanical properties. You don't have to machine off any ingates or feeders or anything like that. Plus, you can do bimetal castings by having one metal that is less dense than the other metal. Go back to that real quick. All right, so plus you can do bimetal castings by having one metal that's less dense than the other metal. And applications of this will be if you want a hard outer layer and then a more ductile inner layer, so a layer with a little bit more flexibility. Now, our next process is called investment casting. And investment casting is a little unique from some of the other casting processes we're talking about so far. Investment casting is not a permanent mold casting process, but the reason why we talk about it in this section is because it gives you the high dimensional accuracy and other properties that a permanent mold will give you. Now, this is also called the lost wax process. You remember we had evaporative casting called the lost foam process. And so obviously what will happen in this case is that you'll be using wax and then the wax is going to go away. So exactly how does it work? Well, you initially have a pattern that is made of wax, and that is typically done by a die casting process. So plastic injection molding, which is a die casting process. And then what happens, you coat it or invest it. That's why it's called investment casting, because that coating process is called investing. You coat it or invest it with a thick layer of refractory material. Remember that refractory material is material that protects it from very, very high temperatures. And usually this is sort of a kind of slurry with some ceramic as part of it. Now this mold slurry is poured in around the pattern, and the pattern is melted and poured out. So that's where the lost wax comes from. The wax pattern gets fired, melted, and is poured out, leaving that open mold cavity. Okay, the mold is then preheated, and the metal is poured in. Now, the mold is preheated very importantly because you don't want the molten metal to be heating that mold at different rates in different places because it's going to damage the mold. So you want the mold to be somewhat the same temperature or close to the same temperature as a molten metal. And so that's why you're going to preheat that. And then after it solidifies, you just break the mold away. And so that's why it's not a permanent mold process, because you break the mold away. Now let's start in the middle. Let's start this at the beginning.
The first stage of the process is to produce an exact replica or pattern of the required casting. This is made by injecting wax into a die. The wax pattern is then assembled onto a wax feeder system. Each assembly or tree may have just one large pattern or many small patterns. The wax assembly is then dipped into high-grade ceramic slurry by a large robot. This is the most important coating, as the metal will lie next to it when poured into the mold. Whilst the thin slurry coating is still wet, larger particles of ceramic are dropped onto the wet surface to build a thicker coat. After drying, this coating process, or investment process, is repeated several times, building a shell mold thickness appropriate to the size of casting and metal to be cast. After the finished shell mold is dried, the wax is melted out in a steam autoclave, hence the name lost wax process. The molds are fired at over 1000 degrees centigrade to remove any remaining wax and to strengthen the mold. Molten metal is then poured into the molds whilst they are still hot, enabling the metal to run into thin wall sections. After cooling, the ceramic shell mold is broken away, and each casting is cut away from the feeder system. The castings are carefully fettled, blasted, and heat treated. A setting operation may also be required. Material testing, X-ray,
Okay, I'm going to stop here right there
or machining can.
because it's just talking about all the post-processing it has to do after the casting process. So let's move on and look at some of the advantages and disadvantages of the lost wax process or investment casting. So advantages, you can have unusual and non-symmetrical shapes that can be made. It can obtain very, very smooth surfaces and high accuracy. And it can do this for non-machinable alloys. Now, what I mean by non-machinable alloys, it's talking about alloys that are very, very hard, and so they're difficult to machine. So these can be cast with high precision, all right? And it can also do alloys with high melting points. Usually, non-machinable alloys are alloys of high melting points, but it can do both, okay, with high precision. So that's very good for investment casting. Now, investment casting is not suited for very large parts, so you won't find huge parts that are investment cast, but you will find a lot of these parts used in the automotive industry, aerospace industry, any industry with high performance and that needs parts with very, very tight tolerances. And also needs parts which are very strong, which means they will be non-machinable or they'll have high melting temperatures. The next type of permanent mold casting process we talked about is called slush casting. Now, slush casting is really is not a very precise method of casting, and it's used primarily for ornamental or decorative objects as well as for toys. Okay, you have thin walls is what you're making. Essentially, molten metal is poured into the mold, and then you let it stay there, but you don't let the mold completely solidify. You turn it upside down, and then what's left over is going to be just a little layer inside the mold cavity. Now, only low melting point metals can be used for this, and it does have very low dimensional accuracy. So, as I said before, it's used primarily for ornamental and decorative objects, also toys. And here's that process. So this would be an example of a mold, and then you'll go ahead and pour the molten metal into that mold, but you don't let it solidify all the way, just to solidify so that there's a layer that's solid. And then you turn it back over, let all the rest of the liquid metal come and stream out. Our next casting process is called die casting. Die casting is another permanent mold process. And what occurs in die casting is you have a mold with two halves. Typically, the mold is made up of some type of very, very strong and hard metal. And the reason why these molds need to be so strong is because they're injected under extremely high pressures, from 1,000 to 100,000 pounds per square inch. So other characteristics are you have grooves in them to permit that gas to escape, because of course that is very important. And these gateways to the actual mold cavity, they're trimmed off later on. In addition, with being trimmed off with the sprues and also the runner and gating system. Now, these dies are extremely expensive. They're usually machined out of hard metal. That's why they are so expensive, up to $100,000, I'm sure more. And so this process is really only economical for mass production. Only economical for high production rates and mass production. But it does give very high dimensional accuracy and very good surface finish. Now, there are two types of die casting machines normally used. One is a cold chamber die casting machine, and that means that you have your injector is outside of the molten metal. That's why it's called cold chamber. And the reason why is that this molten metal is just too hot to have the injector inside it. So it has to be outside of it. And then usually what happens, you'll either suck or dip some metal here and then pour it in your injector, and the injector will go ahead and inject it into the mold. And that was a cold die casting. Now you also have the hot die casting machine. This is hot die casting because your injector is actually in the metal, so your injector is going to be considered hot. Now keep in mind that a hot die casting machine can only cast metals with low melting temperatures. All right, I know that seems kind of backwards, but that's the way it is, and that's just because the nozzle is buried and embedded into the molten metal. Now let's talk about molten safety for a little bit because we really have not discussed that yet. When you do think about molten metal safety rather, what do you think about? Well, one of the things that might come to your mind is that, hey, you don't want spilling or splashing. You don't want this very, very hot molten metal to spill or to splash on you. And so to keep that from happening, you're going to have to wear protective equipment, including safety glasses, face shields, hard hat, motors, boots, and gloves, leggings, aprons, things like that. Now, another danger is that if you pour molten metal into a huge vat of water, you're okay. But, well, before I go to the but, this is an example of what happens there. So they're pouring molten aluminum into a large container of water. So nothing really happens dangerous. It just looks nasty. All right. Now, this is an example of something that can happen if you put molten metal which has just a little bit of moisture, a little bit of water vapor. Okay. If your mold rather has a little bit of a water vapor still on it, and that molten metal comes in contact with it, what happens is a situation called metal pop. And so the water that it comes in contact with expands very quickly from the heat and causes everything to pop out, which is exactly what happened here. So this guy was actually taking some scrap metal that still has some moisture in it, and then when you put it in the furnace and it got heated up, air expanded and everything popped all over the place. All right, let's think about what do you consider when talking about designing for the casting process and some problems that you sometimes run into. Well, things that you consider is that you consider the weight of the casting mold, of the casting on the mold, and also the strength. You want to make sure you have an effective gating and a sufficient riser so that all your molten metal can get where it's supposed to get to, and that all of your cores are placed correctly. And now, depending upon your casting process, you want to match that to the required dimensional accuracy you need for your part, including your radius, your thickness, all that good stuff. And of course, we cannot forget about shrinkage. And so shrinkage still occurs. That is, you have machine allowance, and then you also have that allowance for shrinkage. So that means that your molten metal is going to shrink down, and so you need to make your pattern that much more bigger so that your pattern can shrink down to the same size as your final product. Now, sometimes cracking can occur at sharp corners, and so you'll see a lot of casting products that will have curves, so chamfers or fillets. Can't remember which one it is, if it's a chamfer or a fillet, but they'll have curves instead of straight corners. All right, especially at where thin sections are. So an example is this wheel right here. You see here it has a curved corner instead of a straight and angled corner, right? And that's a result of designing for casting purposes. Sometimes you might want to add chills, and chills are things that help you control the rate of solidification, okay? And they do that by controlling the temperature. All right, so this was part 2 of processing of metals casting. Thank you very much. Of course, if you have any questions, you can always go by and email me, or you can, if you want to talk to me, you can set up a video conference. Bye.